This is another video by Only Keypads. In this video I simply titled it I2C Basics 101, and instead of making one long video, this video I'm breaking down into partitions, so there's probably about 8 of them. I feel I can present the information a lot better if I break it down into partitions in one big long stretched out video. And what this video is going to consist of is I'm working on a design change for my 4017 Chaser encoder board here, and right now there's an Arduino that does the I2C communications to this PCF8574 IO expander and this AT24C02 EEPROM. And what I want to do is I want to embed a microcontroller right on this 4017 Chaser board and eliminate this Arduino. And the microcontroller I like to go with is a PIC microcontroller, but if I want to use the I2C libraries, I'd have to go with a PIC similar to what I'm showing here. And you can see this is a 40-pin device. It's quite large. There's an SCL clock line, there's an SDA data line, so the library could be used on this particular PIC. But to embed something of that size onto this board, I'd have to increase the size of this board, and that's something that I don't want to do. So what I decided to do is I'm going to go with a PIC 16F676 14-pin microcontroller. But as you can see here, port A and port C has no I2C capabilities. There is no SCL pins or SDA data pins, so I can't use a library on this PIC. And what I'm going to be doing is I'm going to be custom coding an I2C communications between this PIC and my 4017 Chaser board, and this way I can embed that PIC onto the same footprint board that I have here. Okay, so I just wanted to give an idea of why I'm creating this video. And as I'm moving along here is I'm working right now with the communication link between the PIC and the PCF8574 IO expander, and I just want to share some of the information with other hobbyists out there on how I'm developing this I2C code to communicate between the PIC and this IO expander, because I think it might come in handy maybe for some hobbyists to create other projects off of. So with that, I'll get going here, and I'll go to the next partition. In partition 2 of the I2C Basics 101, I just want to present an example circuit that a hobbyist could use with the information that I'm going to be presenting in this video. And if you would take a basic circuit like this, here's the PIC 16F676, and here's the PCF8574, and the PCF8574 IO expander has 8 ports on it, 0 through 7, and basically the code on the PIC will be communicating I2C to this PCF8574. So if one of these switches out here are closed, okay, it will send an interrupt to the PIC, and then the PIC will start to read this PCF8574 port data, and once it gathers all that data and it processes that data, it maybe will trip a relay up here to light a security light or something of that nature. So I mean, this is something very basic, okay, but with the information that I will be presenting in the rest of this video, this is something that can be built off of that information. I'm using it for the keypads, but there's other uses for this. So with that, I'm going to move on to the other partition. This is partition 3 of I2C Basics 101. In this partition I'll be presenting the SCL and SDA driver circuit that's required to do this switching on the I2C bus. And I made a simplified drawing here where I'm showing the PCF 8574 and the PIC. And there's a pull-up resistor here tied to +5, and one of the purposes of this resistor is to prevent a short circuit on this SDA line between +5 and ground. So if either of these switches would be closed, there's always some form of resistance here. So that's one of the purposes of this pull-up resistor. And with both SW1 and SW2 open, there's always going to be a +5 volts maintained on this bus. So as long as there's a +5 volts maintained there, there's no chance of any transient data signals getting onto this bus. So that would be another reason for this pull-up resistor. Okay, and for the PIC to write data to the PCF 8574, okay, S1 will be switched off, which means it will be open to send a 1, because when it's open, the bus is connected to +5 volt, so +5 will send a 1 to the PCF. If the PIC wants to send a 0 or a low, this switch will close. It will clamp the bus to ground, and it will send a low to the PCF. Okay, and the same applies for the PCF to send data to the PIC, except SW2 would do the switching. Okay, so when the PIC wants to read data from the PCF, this SW2 will start switching on and off to send that data to the PIC. Alright. Okay, in this other example here now, I replaced these two switches with two FETs, field effect transistors, and this is a more practical version of what would be inside of this PCF to do the switching. Okay, and the same applies. These FETs will just switch on and off to send a low or to send a high on the SDA line. Okay, this SDA line I'm showing could also be the SCL line, because there's going to be a similar circuit just like this on the SCL bus, but I'm just showing the SDA bus here for simplicity so I don't confuse things too much. Okay, now on the project that I'm working on, this PCF has built-in switching capabilities on the chip, but the PIC I'm using does not. So I have to replace this internal FET that I'm showing here with an external switching transistor. Okay, so this is the reason I'm showing this drawing here, because when I get to the schematic, you're going to see there's going to be 3 transistors external to the PIC, and one of those transistors is to do the switching of the SDA line, and the other transistor will be switching the SCL line. And the other transistor, the third one, I'll explain that when I get to the schematic. It's kind of hard to do that right now. Okay, so that's basically all I wanted to show in this partition. So when I get to the schematic, you have a more visual of why I have those external transistors. And with that, I'll move on to the next partition. In partition 3A of I2C Basics 101, this is basically a supplemental to partition 3. I just want to go over some I2C protocol before I go any further here. And I'll come up with this schematic here first, this drawing right here. Okay, in a basic UART connection, okay, it's known that traffic travels one way on the data buses, transmit to receive. But in I2C data transfer, it's a little bit different. The PIC generates the clock signals. They travel one way on the SCL line from the PIC to the devices out on the line. But the SDA line, traffic travels both ways. Whether the PIC wants to write data or read data, data can go either way. Okay. And in this next drawing here, I want to show that the SDA line has to stay stable during a high clock pulse. Okay, in other words, when the clock pulse is low, the SDA line will be set either high or low depending on what data bit it wants to send, either a high or a low, and then it will clock that data bit, whether it's reading or writing that data bit. Okay, and then the clock line will go low again, and the SDA line would then change state again, whether it wants to set a high or a low. In this case, it wants to send a low, and then it'll clock that data bit out on to the SDA line. Okay, because if for some reason while this clock pulse is high, this SDA line changes state, okay, that's known as a control command, and I'll get into that right now in this next one here. Okay, you can see here that both SDA and SCL lines are high. Okay, in order to initiate a start command from the PIC to let the PCF know that it wants to communicate, it's going to set the SDA line low first, and then after that it will set the SCL line low, and that's a start command. Okay, and then after that it will start to send out these address bits. Okay, it will send out these 7 bits along with a read write bit. Okay, and then once the PCF receives that and everything is okay, it acknowledges it, it's going to send this acknowledge bit back to the PIC, and then the PCF will start sending out these data bits. Okay, and then after the PIC receives these data bits, it will acknowledge to the PCF that it received those data bits. But I'm not using this acknowledge bit in my program. Okay, I'm going right to the stop command, and you can see the SCL line is high right now, and while it's high, this SDA line goes from low to high, and that indicates a stop command. Okay, so I just wanted to kind of clarify how data is sent based on the clock signals, and how the control commands are sent based on the SDA and SCL clock signals. Okay, alright, with that I'll move on to the next partition. In partition 4 of I2C Basics 101, I'm going to be going through the circuit schematics, but before I do that, I just wanted to give a visual of the breadboards. This upper breadboard contains a dip switch package, the PCF8574, PIC microcontroller, 3 transistors, and on this lower breadboard is an Arduino, and the only purpose for this Arduino is to provide a serial monitor so I can see what's going on this board. Okay, so with that I'll get into the first schematic. Okay, in this first schematic I have the PIC microcontroller, PCF8574, dip switch package, and 3 transistors, and basically some resistors and some LEDs. That's all this circuit consists of. One side of the dip switch package is tied to ground. The other side goes to the ports P0 through P7 on the PCF, and they're also pulled high through some pull-up resistors here. Okay. On the PIC, you can see that the emitters on these transistors are tied to ground. So to send out a low clock pulse on this SCL line here, okay, I have to send a high out on pin 5, because I have to bias this transistor on to send out a low on the SCL line. And the same applies to the SDA line. To send out a low on the SDA line, when I'm sending out the address byte, I have to send a high at a pin 6, bias this transistor on to send out that low. And of course I got to bias them off. Okay, Alright, which means I'd have to send lows out of 5 and 6 to set either of these two lines high through the pull-up resistors. Okay, so this might seem a little confusing at first, but that's the way I put it together. But that has to be brought up because the code has to be written accordingly, and basically opposite of what wants to be transmitted out of these two lines. Now this line here, the SDA line, this is used only to when the PIC wants to read the data from the PCF. So the PCF will send that data bit out on this SDA line, okay, and it will either bias this transistor on and off accordingly, whether the bit is high or low, and of course then it would send either a high on this pin 3, or it would send in a low on this pin 3, and that would be the data bit going into the PIC. Okay, and then the PIC will process that bit accordingly. Okay, so basically that's the reason I have these three transistors, and I kept the read and the write transistors because I didn't want to be using this common data line to try to transmit data in both directions. This kind of simplifies it in the coding. Okay, so that's the reason I did that. Alright, and there's some LEDs here. This is just an LED that reads the SDA line of flash accordingly, highs and lows. The SCL line will read the clock high and low. This is an idle LED here, let me know that the PIC is up and running. Okay, this is a green interrupt LED, let me know when this PCF sends an interrupt down, that LED will turn on. These two lines here, 9 and 10, go out to the Arduino. Okay, this pin 9 is the SCL clock echo. Basically it's just echoing this clock pulse down to the Arduino. And this is pin 10, which is the data line going down to the Arduino. Okay, it just mirrors the data that's coming in to the PIC and sends it down to the Arduino. This white LED turns on when the PIC reads the port that changed state. Okay, so I can actually count these clock pulses and know when this LED is supposed to turn on depending on which switch was tripped here and which port changed state. Okay. Alright, and I have a schematic here of the Arduino, which is pretty simple. This is the SCL clock line coming in. It goes to a transistor. I use a transistor to get some line isolation between the PIC and the Arduino. Okay, so this transistor would just flip on and off accordingly with the SCL clock pulses coming in. The SDA has a transistor on it for isolation, and that would just switch on and off depending on the highs and lows of the data that the PIC is reading from the PCF. And when the Arduino sees a clock pulse coming in on a read cycle from the PIC, then it will set up an interrupt in here. Okay, I'll explain that in the Arduino code when I go through it. And there's some LEDs here. This is just another LED that flashes according to the SCL line. This is a data read LED. Okay, this one here is basically like that white LED on that I showed you just previously here. This will turn on when the PIC reads that port that changed state. And this is another idle LED here that just lets me know this Arduino is up and running. So this circuit here is pretty basic. Alright, so with that I'll move on to the next partition. In partition 5 of I2C Basics 101, I'm going to go over the PCF 8574 addressing, and I'll start with this diagram here first. Okay, this is the PCF 8574 pinout, and you can see there's three addressing pins here, A0 through A2, and either of these pins will be tied low or tied high, okay, to set the address for this device. Okay, and in this diagram here I'm showing those three pins, A0 through A2, Okay, and internally there's 4 other additional bits, okay, A3 through A6. Now this is going to be different than if you're setting for a library. If you would set for a library, this A0 through A2, you would tie them all to ground to address the PCF as hex 20. If you wanted to address it as hex 21, you would set A0 high and A1 and A2 low. That would give you an address of 0x21, and so forth and so on here. Okay, but in the library, the read-write bit is somehow handled differently, okay, than just the address byte that you're putting in, okay. But in what I'm doing here is I have to write all of these 8 bits down along with when I write the address byte, okay. So if my device would be addressed as 20 in the library, okay, it would be addressed as, if I'm going to read data from the PCF 8574, I would have to set the address as 41 in my code, because I have to take into account this read-write bit. And if I'm going to write, okay, to the PCF, this bit will be set to low. If I'm going to read, this bit will be set to a 1, which would be a high, okay. So I'm going to be reading, okay, so this bit would be set to a 1, okay. So it would be 41. This would be, okay, 1, 2, 4, 8. That would be the first 4 bits, okay. So that would be the 1, okay, and then I'd have 1, 2, 4. This would be the 4, okay. So I'd have to set it for 41. Okay, if for some reason I wanted to write down to that PCF, I'd have to set it as 0x40, because then this bit would be set low, okay, which would be a 0. So that would be, you know, all zeros here, so it would be a 0. And this one would stay a 4, because it would still be 1, 2, 4, because these are set in the PCF. These cannot be changed, okay. I tried researching and finding out what they actually do, but I could not find anything on it, so just take it as these cannot be changed, and that's just the way it is. But the only ones we're concerned about is this read-write bit and these 3 address bits here, okay. And I put it here, these are jumper selected, okay, by those pins on the PCF, and these are all fixed, okay. So I wanted to bring that up because it's different addressing than if you're using a library, okay. Alright, so with that I'll move on to the next partition. In partition 6 of the I2C Basics 101, I'm going to be going over the PIC code, and I'll bring it up here. In the first part of the code, this is just setting some of the program parameters for the PIC in this section here. This sets the frequency of the clock. Down here I'm defining the port pins on the PIC, okay, the RC zeros, 1s, 2s, the RA port, okay, and I'm giving them some names on each of those ports, okay. I'm just defining them. Here is where this integer PCF ADR, this holds the address for the PCF 8574 as 0x41, okay. This just initializes a variable that I'm using in the program for temporary storage. Okay, in this void main, this initializes the ports on the PIC, okay, whether they're inputs or outputs, okay, that's what that's doing. And here I just condition the LEDs when I boot up the PIC, okay. I'm turning all my LEDs off. I want to make sure they all get turned off. That's all that's doing. Okay, then it goes into this while loop, and this while loop will keep running. It just keep looping, and it flashes that amber LED, that idle LED, to let me know that the PIC is up and running. Okay. And it also checks to see if there's a interrupt on the PCF8574. If one of the ports change state, it's going to send an interrupt here. Okay, and when that occurs, it's going to call this function, this I2C function. Now it would jump out of this while loop, and it would jump down to this function here. Okay, I2C, call I2C. Okay, and this would be the first frame I'm calling of what's going to happen here. This is going to be the routine to write the start bit to the PCF. Okay, because the PIC saw the interrupt come in from the PCF. Now the PIC is going to have to go out and read that data from that PCF. So it has to initialize a start bit, okay, to let the PCF know that it wants to communicate with it. And these first two lines, this is just some line conditioning. Okay, this sets the clock and the data lines, okay, alright, to high. Okay, it sets T1 and T2 off. Remember, those transistors work opposite what the line is going to actually be. Okay, then I delay 10 microseconds to allow for some line stability. Alright, now here's where the start gets initiated. Okay, alright, the first thing that happens here is the I2C SDA output is set high. Okay, the start bit to interrupt and open the I2C communications. T2 biased on, pulls the SDA line low. Okay, we're going to pull the SDA line low before we set the SCL line high. Alright, I'm just going to bring this other diagram up here when I get to it here. Okay, if you remember back here, the SDA line has to go low before the SCL line goes low to initiate the start. Okay, and that's what this is doing here. Okay, so after the SDA line goes low, we're going to delay 10 microseconds, and then the SCL line will go low. Okay, and now that's going to initiate the start. Okay, then it's going to jump down to the second frame, and this is where the PIC is going to send out the address byte to the PCF. Okay, alright, the way it does it is it's going to take that address of 0x41, because again, remember back here, I'll get this up here in a second, I address the address byte as 41 because I want to read data from the PCF. So I have to take all of these 8 bits of this byte, and it's going to be a hex 41. Okay, alright, now what I do is I have to read the most significant bit first of that byte. Okay, so let me bring this back up here real quick. I have to send this bit here out first. This is the most significant, and this is the least significant. Okay, so I'm going to start with this bit, and then I'm going to decrement 7, 6, 5, 4, 3, 2, 1, 0. Okay, this would be location 0, if you will, and this is location 7. Okay, so if the PCF address, okay, bit 7, okay, ends with a 1. Okay, so if this bit here would be a 1, okay, the bit in this location, okay, it will set the SDA line high. Okay, so it has to turn the transistor off, okay, to set the line high. Okay, if it's a 0, okay, which it is, because this is the 7th bit in hex 41, this is in its binary form. Okay, this is in the hexadecimal form. Okay, it's going to set the line low, so it's going to, okay, it's going to turn that transistor on and set the line low. Okay, Alright, then it's going to jump down to a clock routine because I have to clock out to the PCF, so the PCF reads that bit on that SDA line. It's going to look for the clock pulse because remember the PIC controls the bus, okay, and the PCF responds to the clock signals. So the SDA bus right now is set low, but the PCF is waiting for this clock signal to read that low. Okay, and then it's going to jump down to this clock routine down here. Okay, and this is where it sets the clock line high. Okay, and then it'll delay another 10 microseconds and then set the clock line low. So that's one clock pulse. Okay, and then after it leaves this loop, it'll jump back up here again. Okay, and it'll go down and it'll start reading this next loop, okay, which is bit 6. Now it's going to read bit 6 and it's going to AND, okay, bit 6 with 1, okay, and depending if it's a 1 or a 0, it's going to set the bus accordingly, the SDA bus, and then it's going to jump down and it's going to clock that out to the PCF, okay, to tell the PCF to log that bit. Okay, and this same routine goes on for the whole address byte. There's bit 5, 4, 3, 2, 1, and 0. This is the read-write bit here. Okay, that's bit 0. Alright. Okay, so after it's done with that, it's going to release the SDA line because it has for the PCF 8574 to send the acknowledge back to the PIC. Okay. Alright, so that means it has to turn, okay, the SDA line pull-up resistor set high, so T2 is biased off. Okay, it sets the SDA line high. I'm going to just bring up another diagram here real quick. Let's explain it better. Okay, this is the SDA line that the PCF is going to send that acknowledge bit out on, this SDA right here, and then it's going to either turn this transistor on or off, okay, but I have to set this line high here, okay, so that the PCF then has control of this line right now, so it can either, you know, leave it a high, okay, through the pull up, or if it wants to set it low, it can also set the line low, because if I have SDA here biased off, okay, this SDA line, okay, is going to be low, okay, right through here, and PCF could never switch this line, okay, to a low or a high, okay, so that's why I have to release the bus, okay, I have to release it high so the PCF can take control of it. Okay, that's what I'm talking about when I say that I have to release the line. Alright, and after I do that, okay, I'm going to delay 50 microseconds just to allow the PCF to drive the SDA line high, because to drive it low, because a low is going to be an acknowledge. If it drives it high, it means it didn't receive the address byte correctly. If it received the address byte correctly, it's going to drive the SDA line low. Okay. Alright. Okay, then I'm going to have to clock the SCL to verify to the PCF that the acknowledge was received. Okay. Alright. So I'm going to have to SCL line pull up resistor set high. T1 is biased off. Okay. It sets the SCL line high. Delays 10 microseconds. Okay, and if the slave data is equal to 0, it'll look at that acknowledge bit that came in. Okay, if it's equal to 0, it's going to light that blue LED. Remember I had a blue acknowledge LED on the breadboard? Okay, and if it's not, then the LED just won't go on. Okay, alright, and then down here it's going to condition the SCL line low again, okay, because I set it high, now I'm going to set it back low. That's one clock pulse. Okay, and that's all that does here. It just sets it turns the T1 on and sets the SDL line low. And I just delay another 10 microseconds. Okay, then I'm going to jump to a another function to read the data from the PCF8574. I got to read that data now. Okay, so when the PCF sees this clock pulse after it sent out the acknowledge, it knows that the next step is going to be to read, that the PIC wants to read the data from it. Okay, so it's going to set the SDA line for the most significant bit of the ports, which is P7. It's going to send that bit out first if that port is high or low. Okay, and it's going to jump down to this read slave function here. Okay, and this is where it begins to read the data from the PCF 8574. I just have a for loop here. Okay, it's going to run this loop 8 times because it has to read all 8 bits from the data byte coming in from the PCF. Okay, alright, so what happens here is, okay, it just goes through 4, I equals 0, okay, I less than 8, and then I'm going to increment 1 on every loop through here. Okay, now the first thing I do is I set the SCL echo. Okay, this is the echo line that goes out to the Arduino. Remember I said I'm echoing the SCL line. I'm going to set that low. I'm just conditioning that out to the Arduino. Alright, okay, and now I'm going to clock. I'm going to set the SCL line, pull up resistor, set line high, T1 biased off. Okay, because I want to clock in that first bit that the PCF put out on that data bus. Okay, alright, so I'm going to set the clock high. Okay, then I'm going to read that port bit, okay, from the PCF, okay, be it at transistor. Okay, if the slave data, okay, is equal to 0, okay, that this checks if the port bit that came in, if it's low, it's going to light that white LED that I had on the breadboard. Okay, alright, and then it's going to send the SCL clock echo because the SCL line is still high. Okay, it's going to send that out to the Arduino. Alright, because if I go back to my schematic here, okay, you can see that this white LED, okay, is tied to pin 10, which is RC0. Okay, but it's also tied to the Arduino. Okay, so the Arduino sees the same data bit that this white LED sees. Okay, so what happens is the PIC will send out that echo on SCL line. It's going to interrupt the Arduino. The Arduino knows that there's a bit available to read, and it's going to read that bit that's coming in on this I/O point. Okay, and then it's going to log it. Okay, that's all that's happening here. Okay, alright, alright, okay, and if the SCL, we're going to set the SCL line low, T1 biased on. Okay, which means that that's going to be the other side, that's going to be the falling edge of the clock pulse. Okay, we're going to delay another half a millisecond. Okay, and then we're just going to condition that LED off, again, the white LED. But notice here that on the data reads, reading 1 bit every half a second. So you can see how I slowed this data read down. Okay, so I can actually see these bits coming in one at a time because I'm going to log 1 every half a second of the 8 bits. Okay, so you're going to see that when I do a demonstration on the circuit actually operating. I'm going to be able to actually count the number of pulses, okay, of the clock, and see which port on the PCF went low. Alright, so that it's going to light this white LED up. Okay, it's going to be interesting to see that because you always hear that I squared C, you know, it runs high speed 100 kbits per second, but I really slowed this down so I get some visual on it. Okay, so after this loop runs, it's going to run that. It's going to log all 8 data bits, okay, from the PCF. All right, and then it's going to just set the echo low, okay, to the Arduino. That's all that does. Okay, and then I'm going to exit. Now I gotta send a stop command out to the PCF to say that's it. I'm done reading. I'm finished. Okay. So it's going to jump up here and it's going to do a stop command. Okay, and if you remember back, to do a stop command, let me get here once. Okay, the SCL line is high, the SDA line is low, and when the SDA line goes high while the SCL line is high, that initiates a stop command. Okay, so we have to set the SDA line low and the SCL line high, and then trigger the SDA line high to initiate that stop command. Okay, so that's what that is doing here. Okay, SDA, set the SDA line low to prepare for the stop command. T2 biased on. Okay, then the SCL line pull up resistor set high, T1 biased off. So the SDA line is set low, the SCL is set high. Then the SDA line pull up resistor set line high, T2 biased off. Now it sets the SDA line high. So that's going to initiate the stop command, okay, to the PCF, so it stops communicating. Okay, and that's it, and that's the end, basically of that whole loop. Okay, and then it'll jump back up and it'll just start running this while loop again, waiting for the next interrupt to come in. Okay, it's just going to keep running this loop again, and once another interrupt comes in, when it sees a change of state on one of the ports of the PCF, it'll run this whole routine again. Okay, so that's pretty much it. Alright, in the next partition I'm going to go over the Arduino code. Okay. In partition 6A of I2C Basics 101, I'm going to be going through the Arduino code, and I'll bring it up here. Okay. Alright, this code is fairly simple compared to the PIC code. I'm just declaring some constant integers here for the LEDs and the SCL, okay, and the data line coming in on the Arduino pins. Okay. Alright, these volatile integers here, okay, I'm keeping these volatile because this T2 data is used in the interrupt routine, so I want to keep it transparent. Okay. This is my serial begin for my serial monitor. These pin modes just declare, okay, these variables as outputs or inputs for the LEDs, okay, and the SCL and the data inputs. This interrupt routine, this 0 here, okay, indicates that my interrupt is tied to pin 2 on the Arduino Uno. I believe there's just 2 interrupt pins on the Arduino. I think it's 2 and 3. If I was tied to pin 3, this would be a 1. Okay, so 2 I'm tied to 0. It has to be declared as 0. This is a function that will be jumped to on a rising edge of pin 2. Pin 2 is the SCL clock echo coming from the PIC. So when it sees a rising edge on that clock echo, it's going to jump to this function. Okay. Okay, in the next section here, in this void loop, this just runs that amber, I'm sorry, it's a red LED to let me know that the Arduino is up and running. Okay, so this loop will just keep running here until it sees an interrupt occur up here. Okay, so when an interrupt does occur, it jumps to this read function, which is down here. Okay, and the first thing it's going to do is it's going to read that pin of where the data is coming in. Okay, I'm going to jump here to another diagram here real quick. Okay, all right. it's going to read this pin here, okay, of this data coming in. So when it saw that echo line coming in, okay, it saw the rising edge because it came in high, okay, it turned on this transistor, okay, and IO .2 here saw a high, a rising edge, and then it's going to jump into the interrupt routine, and it's going to read this data that's coming in on IO pin 3 here on the Arduino. Okay, that's where that's coming into play at here. Okay, it's going to store it in T2 data. Okay, and then the port number, I got to start counting the PCF ports from P7 to P0 because there's going to be 8 bits coming in. So I'm going to decrement them by 1. Okay, up here I set this port number, okay, to 8. Okay, so it's initialized as 8. Okay, so it'll decrement 1. Okay, so it's going to take that as port 7 coming in, and if the data on this data bit coming in is high, okay, that means that the port on that PCF came in low, okay, over on the PIC. Okay, so that would be the one that changed state because it went from a high to a low. Okay, and then it's going to a digital write, okay, my data LED high, okay, which is going to turn on an amber LED on my breadboard. Okay, alright, I just want to back up here a second because I want to show something here so it's not too confusing. Okay, see, this is the IO data port that goes into the Arduino. So when the PIC sees the port that changed state up here, okay, it sends a high out here, okay, because this white LED turned on, if you remember. Okay, so that same high is being sent to the Arduino, okay, indicating that it read the port that changed state up here. Okay, that's what that's doing. Okay, alright, and then what it's going to do is then it's just going to send out to my serial monitor. It's going to print the hashtag, it's going to print the port number, okay, which will be, okay, this port number here, which would be 7, because it reads that port 7 first, which is the most significant, and then it'll say the data is low. Okay, that's the one that changed state. If not, okay, alright, it's gonna digital write data LED low. Okay, turn the amber light off. It's going to keep that amber light off because it didn't see any change of state. And then it's going to print out to the serial monitor the port number and that the data was high. Okay, alright, okay, and this will just then the port number isn't equal to 0 yet, so then it's going to it's not going to run this if routine. It's going to jump out of here now and it's going to go back up, and it's just going to keep on reading that void loop here and keep on flashing that LED until the next interrupt comes in. And when the next interrupt comes in, okay, it's going to again, okay, read that data coming in, okay, and store it in T2 and then run this routine again. And that's all this does. Okay, it's a very simple couple of loops here. Alright, okay, so with that I'll be going into the next partition, which is the actual demonstration. Okay, in partition 7 of I2C Basics 101, I'm going to demonstrate how the circuit actually works. And I'm going to bring my camera up here, okay, so it focuses in. Okay, these are the two breadboards. This is the PCF 8574 dip switches, PIC controller. Okay, the LEDs here, this is that amber LED flashing. Okay, that's the idle LED. This blue LED here, okay, this is the acknowledge LED right here. There's a green LED back here, that's going to be the interrupt LED. Okay, there's the data LED here. This is the LED that's off of the T2 data line Okay, this is going to be on coming out of the PIC, that data line. So this is only going to be used when I'm sending the address down. Okay, and this is the SCL line, this green LED. Okay, and over on the Arduino, I got a blue LED here. That's the Echo SCL line coming in. This is that red LED, that idle, that lets me know the Arduino's up and running. And this is another data LED. This one will come on when it reads the bit that changed state on the PCF 8574, and there's also a white one over here that's going to do the same thing. It's going to turn on when the PIC reads that port that changed state. Okay, so I'm just going to show this here. Okay, I'm going to be reading port 7 to port 0, so I'll be able to count the clock pulses. Okay, if I'm triggering port 7, it's going to be it's going to be on the first clock pulse if that's the one that changed state on the PCF 8574, then either that white or that amber LED will come on the Arduino, and so forth and so on. So I'll be able to count down. Okay, and I'm also going to have my Terraterm emulator to tell me which one of these changed state. Okay, so I'm just going to do a little bit of a demonstration here. Let me get my Terraterm up here. Okay, that's up and running. Alright, I'll put that over here as far as I can, get it out of the way. Okay, so what I'm going to do is these diff switches aren't quite in order, like I said earlier in the presentation. So this first one is port 0 on the PCF, then it's 1, 2, 3, okay, and then I have 4, 5, 6, 7. Okay, so say if I trip port 3, okay, alright, so port 3, okay, I'll be able to count 5 clock pulses, and at the 5th clock pulse, okay, this amber LED here will light, and this white LED back here will light. Okay, so let me trip port 3, okay, which is the 4th switch in, and I can watch the Terraterm. It's going to also log it. 1, 2, 3, 4. Okay, here's 1, 2, 3, 4, 5, 6. Okay, on the 5th pulse you saw the amber LED go on, and on the Terraterm emulator you see it says port 3 data low. That's the one that changed state. Okay, so it logged it on the Terraterm. Okay, I'm going to clear this off of here right now. Okay, now watch when I flip it again. You're going to see the acknowledge light come on, and you're going to see the interrupt light come on over here. Okay, 3, 4. Okay, you see it acknowledged. It sent the acknowledge back to the Arduino, and this is the interrupt that came in from the PCF. Okay, and you can see this green one is counting the SCL clock line. Flip that again. See it counting? That green one's counting, and this one's just mimicking it. This is the echo coming over. Okay, alright, then if you watch this amber LED here, that'll come on the 5th count, because I'm going to trip the same one 3. I'm just using the same one right now so it don't get confusing. Okay, so I'm going to count 1, 2, 3, 4, 5 on this blue LED, and on the 5th count this amber LED should come on. Okay, let me clear the Terraterm again, okay, to get this set up right. Okay, so this is 4. Okay, here I go. 1, 2, 3, 4, 5 came on. Okay, see it? And on the Terraterm, P3 is low. Okay, alright, I'm just going to do another one. Okay, and then okay, let's do a P5. Okay, P5 is the 3rd count in. Okay, because we go 7, 6, 5. We're going to count from the most significant bit first. Okay, so it'll be the 3rd count. Okay, and P5 here is this 2nd dip switch in, so it should be 3 counts. Okay, alright, 1, 2, 3, 4, Okay, and you can see on the Terra term it says port 5 data low. Okay, so it counted it properly. Alright, and I'll just do another one. Then I want to show something else here. I just want to show this, that this works. Okay, I don't know, let's do a P1. Okay, P1 is going to be 7 counts. Okay, 7 6 7 6 5 4 3 2 1. Okay, it's going to be 7 counts down. Okay, so P1 is the second dip in here. Okay, alright, it's going to be 7 counts. Okay, 1 2 3 4 5 6 7 8. There it is. Okay, and there it is on the Terra term. Okay, it says port number 1 data low. Okay, now I want to show something else here. And you can see it's counting 1 bit every half second, so I really slowed that data read down. Okay, but then I want to also show this. Okay, let me get my Terra term out of the picture here for a little bit. Okay, I want to look at this red LED because this is the one that is going to that's the data address byte going out to the PCF 85. You're going to see this one flash real fast because this one is running that 10 microsecond clock pulse. Okay, so I have 2 different clocking scenarios in this system. Okay, alright, so I'm going to just flip one of the switches and watch that LED is going to flash real quick. Okay, and then after it's done counting, it's going to send a stop at the same rate. Now I'm going to try to get the green one in there too, so you can see it's actually counting when it goes on. But it's going to be really quick. It's going to come on real fast, that red LED. Alright, so let me flip a switch here. Okay, now watch real quick. I'm going to flip it now. There, see it flash? Okay, that already sent the address down. Now watch when that green LED, watch, see it flash real quick again. That was a stop. That was a stop command. I'll do it again. Okay, now I'm going to flip it right now. Okay, ready? Okay, go. There it goes. That sent the address byte down already. And now it's going to send a stop command. Right there. Real quick. One more time. Okay, let's do it again. Okay, let it go through. Stop command. There it is. Okay, the stop command. I'll do it one more time. There it is. Okay, address byte and stop command. Okay, so you can see that I'm running 2 different timing cycles in this. Alright, so you can't slow the data bus down to see what's going on. Okay, alright, that's pretty much it that I wanted to demonstrate here to show that it actually works. And this project is pretty neat. I mean, if you want to dissect the I2C framework a little bit, build your own custom circuits around it. The next one I'm going to be working on is the EEPROM. That one's going to be a little bit different because I have to access a register before I can read or write the data. So it's going to be a little bit more coding involved there. But when I get that one done, I may do a video on that. I'll see. Okay, but this one here is something for a hobbyist to mess with. Want to learn a little bit about I2C. Okay. All right. Thank you. In partition 8 of I2C Basics 101, this will be the resource partition on where to go and get the schematics and the code for the project. Okay, all you do is just go into your browser, type in onlykeypads.info. Okay, you're going to come to the Only Keypad site. There's pick projects drop down here. This one is on the UART that I did a while ago. This is pretty interesting too if anybody has interest in that one. This is the I2C Basics 101 here. Okay. This page here just gives some basic information on it. Defines the project. Okay. Basic structure of the project. Okay, and these would be the schematics. Okay, you can just open in another page here. Alright, and you can just of course expand it. Alright, this is the schematics for the PIC PCF 8574. Okay, and I'll go down here a little bit further. Alright, this is the one on the Arduino. Okay, you can just open that one. Okay, same thing. Expand it out. Okay, this is the Arduino. Okay, schematic. Alright, everything is pretty simple here. This is just some displays of the serial monitor, what it looks like, and the Terraterm monitor. Okay. On the other drop downs, the PIC code is under this one. Okay, little description there. There's a URL link here. Okay, this brings up the code. This is for the PIC right here. Okay, this is all the code that I went over in the presentation. Okay, and there's also a PDF file here if somebody wants it in PDF. Okay, this is a PDF file here. Okay, and one more thing, there's the Arduino code. Okay, that's going to be on this page here. Okay, again, same thing, a URL link here. Okay, and this is very short, this code. It's only one page here. Okay, that's all the Arduino code. That's all it consists of. And again, there's a PDF file on it here too, if somebody desires PDF. Okay, you can just copy this, and you can just paste it into your Arduino IDE, and the same with the PIC. Just copy it out and paste it into your PIC program. Okay, that's all you need to do. Alright, I hope this presentation is helpful to some hobbyists out there. It's a lot of fun because you're learning I2C basics. You're taking the framework of I2C and you're modifying it to build some custom code. And I hope this helps down the road. And like I said, if I get with the PIC with the EEPROM, I'll see if I can do a presentation on that one, because that's a little bit different than using the PCF. Okay, thank you for watching.